Okay, this is Dr. Martin P. back with the second part of the video on reaction mechanisms, finding the rate law of that overall reaction, first step being the fast step. So we left off, real quickly, I'll just review, we left off making sure the overall reaction was equal to the fast step and the slow step and the fast step, 1, 2, and 3, all added up, which we did, and they are equal to each other, so we're in good shape. Then we found the rate law for the slow step, which is right here in equation number 2. We have a rate constant K2 times the concentration of N2O2 times the concentration of H2, all raised to the power of 1 for each. Okay. Then we looked at the slow step rate law and compared the molecules there with the reactants in the overall reaction. We see that hydrogen is found in both, so we're in good shape, as I mentioned previously, and then N2O2 is not equatable with NO, and we need to get NO into this position here. Okay, so what we need to do now is look at equation number 1, the first step being the fast step. This happens very quickly, and it's in equilibrium. So looking at number 5, the fast step is in equilibrium, and at equilibrium, the rate of K1 here, that's its rate constant, times the concentration of NO raised to the power of 2, its coefficient, equals K minus 1, the reverse reaction, times the concentration of N2O2 raised to the power of 1. So when this reaction goes forward and then reverses and goes backwards, okay, what happens is the rates eventually become equal to each other and the concentrations become constant. So these are now equal to each other. And then being equal, that means that N2O2 is equal to NO. And we want to get NO here, found in the overall reaction, into the slow step here. And we see that N2O2 is found in the slow step. So we can now basically, with a little bit of maneuvering we're going to do, replace replace N2O2 with NO. Okay? So what we need to do is get rid of the rate constant, K minus 1, and we do that by dividing both sides by K minus 1, here and here. And we now have N2O2 completely isolated. In number 6, this is what it would look like. K1 divided by K minus 1 gives you the concentration NO raised to the power of 2, which now equals N concentration of N2O2. So now we have N2O2 totally isolated. And what we can do is take that NO with its rate constants and slip it into the position N2O2. Since N2O2 and N2O2 are equal in both positions, fast step and the slow step, we can slip this in easily into this position with these rate constants. So number 7, since N2O2 concentration of is found in the slow step and is equal to NO in the fast step, we can replace concentration N2O2 in the slow step for concentration NO. So that's what we did in number 8. Now we have a jumble of rate constants. The K2 is the rate constant for the slow step, which is right over here, with the K1 divided by K minus 1, which is how we isolated the product side N2O2, the fast step, times the concentration NO raised to the power of 2, times the concentration of H2. So basically now we have our rate law, okay, for our slow step, and we have NO here and H2 here found in our overall reaction, which is what we're looking for. Now let's just clean these rate constants up. We can take this jumble of rate constants and just make it one simple rate constant K. So in number 9, rolling K2 times K1 divided by K minus 1 into one rate constant K, we have the rate law for the overall reaction. And number 10 tells us exactly what it is. The rate law equals now K times the concentration of NO raised to the power of 2 times the concentration of H2. And you notice that H2 is found in the overall reaction and NO is found in the overall reaction. So we're in good shape. So we just found the rate law for this rate mechanism. You guys have a good day. Hopefully that made some sense. And if there's any questions, certainly message me. We could talk about it.